week 4 of distance learning. All right. Today we're going to take a look at what are called sequences and series, and today we're just going to focus on sequences. Okay, we'll get to series in the next video. Okay, so sequence, what is a sequence? Well, it's just a list of numbers, right? So I'll do a couple examples for you here, right? I could go ahead and have 3, 8, 13, 18, 23, and so on, right? And the numbers just keep going and going and going. That's what this ellipses means here, right? Another example might be if I had 3, 6, 12, 24, 48. And then finally, a last example, and this one's kind of neat. It's 1, 1, 2, 3, 5, 8, and it keeps on going, okay? So these are all different types of sequences that we're going to take a look at, right? So this first sequence here, you've probably already picked up on the pattern. Each time, it's going up by +5, right? So this is what's called an arithmetic sequence. And the reason it's called an arithmetic sequence is there is a common difference between consecutive terms. Now that common difference, we're just going to go ahead and refer to that as D. The common difference here is D. So in this case, D equals 5 because we're adding 5. You can imagine if we're going down by 12, D would be -12 because we're adding -12 each time. Okay? You can always find the difference by simply subtracting two consecutive terms. So for example, if I were to do 18 minus 13, I would get 5. So always just subtracting two terms backwards. Now the second sequence here, right, is what's called a geometric, right? And again, you've probably noticed what's happening here. Each time we're multiplying by 2. Okay, so here this one has a common ratio, which we call R. And you'll study those more later in Algebra 2 when you get to exponential functions. But here the common ratio, right, is just going to be 2. Because if I take any term, 48, and divide the term in front of it, 24, I get 2. Okay. Now this last one's kind of neat. This is neither of those, right? To go from 1 to 1, I add 0. To go from 1 to 2, I add 1. To go from 2 to 3, I add 1. But then to go to 3 to 5, I add 2, right? And then go to 5 to 8, I add 3. So this one's a different pattern altogether. It's not arithmetic. It's also not geometric, right? Because if I do 1 to 1, that'd be times 1. 1 to 2 would be times 2. 2 to 3 would be times 1.5, right? So it's not geometric either. So this is actually a neat pattern where we have 1, the next term is 1, and then to get this next number, we add the previous 2. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. So the next term here would be 5 plus 8 is 13. Okay? So this is actually a neat sequence. This is called a Fibonacci sequence. If you've ever seen the movie The Da Vinci Code, they talk about the Fibonacci sequence. Fibonacci is just a famous mathematician from the Middle Ages. I want to say he was Italian, and he's accredited for this cool kind of sequence here. All right? But we're only interested in arithmetic for now. So we're going to focus in here on arithmetic sequences because they relate really well to linear equations, which we'll see a little bit later. Okay? So the first thing we want to do is we want to talk about different ways that we can express these sequences using a formula. Okay? So we're going to go ahead and take a look at a different one. All right? And we're going to start by saying, okay, right here, if I've got the sequence that's 4, 7, 10, 13, 16, how can I go ahead and express this as a formula? And the way we do this is we do this using what's called a recursive formula, right? So here, to find a recursive formula, the first thing we do is we figure out what the difference is between terms, right? So here to go from 4 to 7, I'm adding 3. 7 to 10, I'm adding 3. 10 to 13, I'm adding 3. So I know that my difference here is going to equal 3. So if you ask somebody, hey, how do you generate this sequence? They might say, well, you start at 4, right? So the first term is 4. And then for every term, you're just going to keep adding 3, right? So for each term, just go ahead and add 3, right? Now, to express this recursively, what this formula is going to look like is we're going to actually talk about these as being nth terms in a sequence. So here, this term is a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. So for the nth term, which is just any term in the pattern, so a sub n, we can say that a sub n is going to equal 4 whenever n equals 1. But for numbers greater than 1, I'm going to take the previous term, a sub n minus 1, and I'm going to add 3 for n greater than 1. Okay? Now this isn't very intuitive, but here, a sub n is the nth term. So a sub n minus 1 is just the term before the nth term, right? So if I follow this pattern, I know that when n is 1, a is 4, right? So a sub 1 would equal 4. Now here, for 2, right, a sub 2, right, because 2 is greater than 1, I'm going to look down here at this part of the formula, and this is going to equal a sub 2 minus 1 plus 3. Now a sub 2 minus 1, well, 2 minus 1 is a sub 1, and we know previously a sub 1 was 4. So we're going to get here 4 plus 3, which is 7, right? And I can keep doing this, right? I can go ahead and say here, well, a sub 3 is going to equal a sub 3 minus 1 plus 3. So that's a sub 2 plus 3. And I know that a sub 2 is 7. So 7 plus 3 is 10. And you can see I'm already starting to generate the terms of my sequence, right? So 4, 7, 10, right? So it's always going to be, again, the same pattern here, 4, 7, 10, okay? And I can use this to generate the next 3 terms of my sequence. And you could have done it without writing this recursive formula, but this recursive formula is going to be important, okay? So here to write the next 3 terms, I could go ahead and just add 3 here. I know this will be 19, so the next term would be 19. Term after that would be 22. Term after that would be 25. Okay, so I can always find the next 3 terms in my sequence. Okay, does that make sense? Now, the reason these recursive formulas are useful is because we can use them to get to an explicit formula. Okay, so here, if we go ahead and take a look here, right, there's a sub n formula. Just to summarize our recursive formula, it's a sub n will always be a sub 1 for n equals 1, and this is our first term, right? And then a sub n minus 1 plus whatever that difference is, d, for n greater than 1. Okay, so these are our recursive formulas in general for a recursive arithmetic sequence. Okay. Now to get an explicit formula, right, what do we want to do? So to get an explicit formula, I can kind of transform this to an equation that looks similar to y equals a mx plus b. So here, a sub n, right, can equal that first term is kind of like my starting point, okay? And I know I'm just going to keep adding the difference, right? So we're going to go ahead and add the difference. The question is, how many differences do I have to add, okay? So if I want the second term, right, I just have to add 1 difference. So I'm going to add 1. If I want the third term, I want 2 differences, right? So it's going to be 3 minus 1 is 2, because I have to add 2 times whatever this difference is. If I want the nth difference, it's going to be n minus 1, okay? So in general, our formula becomes a sub 1 plus d times n minus 1. So there's always 1 less difference than whichever term you're looking for, because we start with the first term, okay? Does that kind of make sense? Now, I don't usually teach it this way. I usually teach it a different way, but this is consistent with what your book sees. The way I teach it, you'll see a little bit later. But what I usually do is I just teach students, hey, what would the previous term have been, right? So even though the pattern starts at 1, I say, well, what would the term before the first term have been? A sub 0. And then I just do plus the difference times the number of terms. Okay, and we'll use that a little bit more later. Okay. So again, I can now translate between a recursive and an explicit formula. Okay. So for example, if I give you the recursive, and I want you to give me the explicit. Okay. So here, the recursive formula I give is a sub n equals, and we'll say that this one starts at 45 when n is equal to 1. And to get to the next term, we take the previous term, a sub n minus 1, and we simply subtract 2. And that's for values of n greater than 1. Okay. So here, if I take a look and I kind of interpret all this, what do all these things represent, right? Well, right here, we've got a sub 1. So here's a sub 1. Here we've got our difference, d, right? So I go right to my formula, right? And I can say, well, explicitly, a sub n will equal the first term, a sub 1, 45, minus 2, which is my difference, times n minus 1. Now, why is an explicit formula useful? Well, recursive formulas are very easy to write, but what if I want the 15th term in this sequence? Well, I don't want to have to sit here and list out all 15 terms. I want to be able to get my explicit formula to figure out what's going on. Okay. We can also go the other direction. All right. So we can also turn around and say, well, how do I go from explicit to recursive? Now your book keeps this pretty easy on you. All right. So explicit to recursive. And maybe they go ahead and tell us, well, here's my explicit formula. A sub n equals 1 plus 7 times n minus 1. Okay. Now, if I want to express this as a recursive formula, right, I've got a few things here, right? I can see, well, hey, this is a sub 1. I know that my sequence is going to start at 1 when n equals 1. And I can see here that 7, right, positive 7, represents my difference. So now I can write my recursive formula, which will be a sub n equals, the first term is 1 for n equals 1. And then every term after that will be the previous term, a sub n minus 1, plus the difference, which is 7. That's going to be for n greater than 1. Okay? So again, I can go recursive to explicit, and I can go from an explicit formula to a recursive formula. Okay? Now lastly, we're going to go ahead and just apply this to one word problem. All right, it won't be too bad. We'll make it pretty easy. All right. So our word problem. We've got an auditorium, okay? And we're told, hey, in the auditorium, we know that the first row has 15 seats. I'm sorry, 18 seats. Okay? And then we're also told in the fifth row, there are 26 seats. Okay? And we're asked how many are in the 12th row. So if the sequence is arithmetic, how many seats are in the 12th row? Okay. Now we can go ahead and we can, figure out what the pattern is and say, hey, what do I have to keep adding to 18 to get to 26 when I get to my fifth term, right? We can do that. But this one's actually going to make more sense to kind of go explicit with it, right? So I know my general form of an explicit formula. What does that look like? Well, I know that a sub n is going to equal a sub 1, whatever my first term is, plus d times n minus 1. Okay? So if we fill this in with the information we know here, right, the fifth row, so we know that a sub 5, the fifth number in the sequence, right, will be the first term in the sequence plus whatever the difference is times 5 minus 1. Now we know the first term, right? The first term here is going to be 18. We know the fifth one is going to be 26, so let's plug in those numbers. So this is going to be 26 equals 18 plus whatever my difference is times 4. And now we can solve this for d and figure out what the difference is, right? So if I solve this for d, I'll subtract 18 from each side. Right? I get 8 equals 4d, and then I'll divide by 4. I find that d equals 2. Now that I know d equals 2, I can write my explicit formula. I have enough information now. Right? So to write my explicit formula, I can put a sub n, the nth term, is going to equal whatever a sub 1 is, which we know is 18, plus the difference, 2, times n minus 1. And again, you might notice how this looks like y equals mx plus b, right? So it's like a linear equation. But here I want the 12th term. So a sub 12 will equal 18 plus 2 times 12 minus 1, because I'm going to have to add 11 of these differences, right? So a sub 12 equals 18 plus 2 times 11. So 18 plus 22 equals 40. So I know there are 40 seats in the 12th row. Okay, so word problems aren't too bad. All right, we're going to pick up in the next video doing series, and series are not too bad. There's some new notation, but it's pretty easy. Okay, email me if you have questions.